there, Math Hoppers! In this video lesson, we will learn how to solve nonlinear systems of equations. So to review, a system of equations is just a set of two or more equations that we solve at the same time. And up until now, every single system of equations we have seen and solved has contained only linear equations. So they've either contained 2 or 3 linear equations. Well, now we have nonlinear systems of equations, and that just means that at least one of the equations in the system will not be linear. So some things will change about the solution of these systems and some things won't. The solution set of a system of equations, whether it's linear or nonlinear, is still the set of all points that make all the equations in the system true. Graphically, it is where all of the equations intersect. Now, what is different for nonlinear systems is that we can have more than one solution. Remember, with linear solutions, we either had one solution, no solution, or infinitely many solutions. Let's take a look at the solutions of nonlinear systems of equations. We could have no solution. Here we have a parabola and a line that never touch. We can have one solution. So we have a circle and a parabola with exactly one intersection point. We can have two solutions. So we have a circle and a line with exactly 2 intersection points. We can have 3 solutions. Here we have a parabola and a circle with 3 intersection points. And believe it or not, we can have 4 solutions. We have an ellipse and a hyperbola with 4 intersection points. We won't have one in this lesson, but you might run across one. Let's review solving just a linear system using the substitution method. And the reason I want to review this method is this is the method we most often use when solving nonlinear systems. So here we have a system that just contains 2 linear equations, and when we use substitution, we look at both equations and we solve one of the equations for one of the variables. So right now, I'm going to solve either this first equation or the second equation for either x or y. And looking at these, I am going to eliminate this second equation. It's a hot mess. There's too many steps to solve for either of the variables. But looking at the first one, if I simply add y to both sides, I will have solved for x. So that's what I want to do. I want to solve x minus y equals 3 for x because it just involves one step. So let's do it. Add y to both sides, we get x equals y plus 3. Now we have this expression, y plus 3, that we can plug into the second equation everywhere we see x. Luckily, we only see one x, so it's not that bad. Remember, when you plug this expression in, you have to put parentheses around it. You have 2 terms, y plus 3. You have to distribute the 3 to both terms. So let's solve for y. Distributing the 3, we get 3y plus 9 minus 4y equals 7. We're just going to combine like terms. 3y minus 4y is negative y, so we get 9 minus y equals 7. Subtract 9 from both sides, you get negative y. Be sure to bring down this negative y. Don't lose your negative sign. Negative y equals negative 2, so there we see that y equals 2. Now we know what y is. That's one of the coordinates we need out of the 2 we need. So we'll plug y equals 2 into the first equation and solve for x. So x minus 2 equals 3. To get rid of that negative 2, opposite of negative 2 is positive 2. Add 2 to both sides, we get x equals 5. Remember that this solution, x equals 5, y equals 2, is an intersection point. So we write the solution as a coordinate point, 5, 2, and we're done. All right, let's try doing substitution with a nonlinear system. This looks messier than it is, trust me. We have 3x squared minus 2x plus y equals 0. That first equation is a parabola. The second equation, y minus x equals negative 2, is a line. So we have as many as 2 solutions here. All right, let's look at this. I see that I have a y here. If I just really think about this, if I solve both of these equations for y, then I have 2 expressions I can set equal to each other. And that's really what I want to do. Now with this first equation, I could just subtract y and negate everything, or I could just subtract 3x squared and add 2x to both sides. But that's really what I want to do. I want to solve both equations for y so that I have 2 y equals. Remember slope-intercept form, and I realize these aren't both linear, but when you have y equals, that's the easiest form of an equation you can have. So I want to get them both into y equals form so I can set them equal to each other. So taking the first equation, 3x squared minus 2x plus y equals 0, get rid of everything with y. Opposite of 3x squared is negative 3x squared. Opposite of negative 2x is positive 2x. So I'm going to subtract 3x squared and add 2x to both sides. I get y equals negative 3x squared plus 2x. Now taking the other equation, super easy, y minus x equals negative 2. Just add x to both sides. You get y equals x minus 2. Now these are the two expressions I'm going to set equal to one another to solve for x. So negative 3x squared plus 2x equals x minus 2. What I'm going to do here might seem odd. A lot of people think, well, it's really easy to just move this x, subtract x from both sides, and add 2 to both sides. But I really don't want to have a negative x squared term when I'm going to solve this quadratic. So what I'm going to do is I'm actually going to move the negative 3x squared and the 2x to avoid having a negative x squared term. So I'm going to add 3x squared and subtract 2x from both sides. When I do that, I get 3x squared minus x minus 2 equals 0. That now is a quadratic. You have learned by now quadratics are never going to go away. So what I'm going to do is factor to solve this. I need to break up my 3x squared into 3x and x, and then I need to find the factors of negative 2 that when you combine them with the 3x and the x, I add up to negative 1, my outer and inner terms. When we factor, we get 3x plus 2 times x minus 1 equals 0. Remember, if you need a review on factoring, go back into our quadratics and solve by factoring and watch that lesson again. Once you have your factors, you set them equal to 0 and solve each of them for x. So 3x plus 2 equals 0, x minus 1 equals 0. Here we're going to subtract 2 and divide by 3. We get x equals negative 2/3. Here we're just going to add 1, so we get x equals 1. All right, so this tells us the x coordinates of our two solutions, of our two intersection points. I have run out of room, so let's move it on up. Now that I have my x coordinates, those two x values indicate two solutions. So what I have to do is plug each x value into one of the equations and solve for the corresponding value of y. Important to note, when you plug x equals negative 2/3 in, that value of y you get goes with this value of x. That is your coordinate point. Don't separate them. So let's do this one at a time. Let's take this equation, y equals x minus 2, because it's super easy to just pop x in and get y. So y equals x minus 2. Instead of x, we put negative 2/3. Instead of 2, I'm going to write 2 as 6/3. We know that 2 times 3 is 6, so 6/3 is 2. Y equals negative 2/3 minus 6/3 gives us a negative 8/3, and that is my coordinate point, negative 2/3, negative 8/3. Okay, now I'm going to plug x equals 1 into y equals x minus 2 and get its corresponding y coordinate. I see that I get y equals 1 minus 2, y equals negative 1. I get the point 1, negative 1. My 2 points of intersection are negative 2/3, negative 8/3, and 1, negative 1. When you check this, you could do it algebraically or graphically. Plug them into your graphing calculator, see your two solution points, use your table to check, play with your little window there because, you know, we have thirds, so sometimes it's hard to check those values. We'll check the next one algebraically. Speaking of the next one, here we have it. Our first equation is a circle, right? X squared plus y squared equals 25. That is a circle centered at the origin with a radius of 5. The second is a parabola. So this means I have as many as 3 solutions. So let's get started. We are going to look and see that both equations have an x squared term. Therefore, I want to take the easier equation and solve it for x squared. If I take this value of y, say you said, well, this is already solved for y. Y is equal to x squared minus 5. Well, then I would have to plug it in here for y and square that value. That value is just too much to square. I don't want to do that. It's much easier to solve this bottom equation for x squared and put y plus 5 up here for x squared. So that's what we're going to do. Solve the second equation for x squared since both of the equations have an x squared term. We'll get x squared equals y plus 5, and we'll plug that y plus 5 into our first equation for the x squared. And then we don't have to square anything. Y plus 5 is equal to x squared, so it just goes in. So we get y plus 5 plus y squared equals 25. Once again, we have a squared term. As soon as you see a squared term, even if it's not x squared, think quadratics. Put it in quadratic standard form, get it set equal to 0. Here we have y squared plus y plus 5, but we have to get it equal to 0. So we're going to subtract 25, which gives us y squared plus y minus 20 equals 0. Again, we want a factor to solve. Factors of negative 20 that add up to positive 1. That's going to be positive 5 and negative 4. Once we have our factors, set them equal to 0 and solve for y. Y plus 5 equals 0 gives us y equals negative 5. Y minus 4 equals 0 gives us y equals 4. So now I have two y values, y equals negative 5, y equals 4, that I'm going to plug into x squared equals y plus 5. Once again, I have run out of room, so let's move it on up. And let's plug in y equals negative 5 first into x squared equals y plus 5. So I get x squared equals negative 5 plus 5, x squared equals 0. Remember, the opposite of squaring is square rooting. So when you take the square root of 0, you get 0. So my x coordinate is 0, my y coordinate is negative 5. The point of intersection is 0, negative 5. Let's put y equals 4 in. X squared equals 4 plus 5. X squared equals 9. Remember, opposite of squaring is square rooting. When you take the square root of 9, remember, all square roots have a positive and a negative answer. The square root of 9 is positive and negative 3. That gives us two possible solutions. It gives us 3, 4 and negative 3, 4. So we are going to check all of these points. We'll check all three into the original system. Where's the original system? Right up there. All right, let's check 0, negative 5 first. So 0 squared plus negative 5 squared, that's 0 plus 25, it equals 25. Now looking at y equals x squared minus 5, negative 5 equals 0 squared minus 5, so negative 5 equals negative 5. That is true. Next point, let's do 3, 4. Let's first make sure that we note that negative 5 works. Now let's try 3, 4. 3 squared plus 4 squared, 9 plus 16 is 25. That works. 4 equals 3 squared minus 5. 4 does equal 9 minus 5. So that works. Looks like 3, 4 is a solution. Now let's check the last one, negative 3, 4. Negative 3 squared, that's positive 9. 4 squared, that's positive 16. Add them together, you get 25. 4 does equal negative 3 squared, which is 9 minus 5. So that's also true. We have three solutions. All of them have worked. All of them check. Perfect. And that's it. That's nonlinear systems. Still have questions? You should be subscribed to our YouTube channel. Submit those questions to us and we'll make you a custom video solution. Till next time, Math Hoppers, take it easy.